Hello, this is Lecture 2 of ComSci 123, Algorithm Analysis. In today's video, we will discuss the RAM model, worst-case analysis, Big O notation, and other asymptotic notations, and how to analyze auxiliary memory. Okay, first, as programmers, we want to write good data structures and algorithms. But what exactly does good mean? Does that mean it's easy to write? Short code? Does it mean it runs fast? Or is it efficient? So what exactly do we mean by good data structures and algorithms? So the two important factors that we are interested in when we talk about good data structures and algorithms are fast running time and efficient memory usage. So this is how we analyze our algorithms. So analysis of algorithms is the theoretical study of a computer program's performance, means its running time, and resource usage. So how does it utilize the memory and the bandwidth, for example? First, let's look at how to evaluate the running time. So one way that we could evaluate the running time is using the experimental approach. So to compare different algorithms, we have to write code for the two algorithms and then run it in a computer and then log the time that it takes to run them. And then we can compare. However, for this evaluation to be fair, we have to use the same platform. So they must run on the same hardware and they must use the same software as well. We also have to test the algorithms on inputs of different sizes. Because what if algorithm A runs fast but only for small input sizes, and actually algorithm B runs fast for input sizes of bigger magnitude. Okay, so we have to use different sizes of inputs. So there's actually a lot of factors that affect the algorithm's running time. And some of these are the following. Number one, input size. So in general, the bigger the input size, the longer it takes to process the data, right? So it will take a longer running time. Next, input structure or content. So a organized data structure could be processed faster by an algorithm compared to an unorganized data structure. So for example, if you are to sort some items, input data that's already close to being sorted will run fast, whereas randomized or a randomized data set will take a longer time to sort. Okay, so input structure also matters. The amount of computer memory also affects the running time, same as the type of computer used. So if we're using a older model of a computer, then it might run slow. But if we use a uh, the latest technology, then it might run faster. The programming language used also affects the running time, and how you implement the algorithm will also affect it. So these 6 factors affects the algorithm's running time. Because of this, the experimental approach cannot really provide you an exact running time evaluation for two algorithms because of differences in platforms or inputs and so on. Okay, so if you use a different setup in hardware or software, one algorithm might run faster, but it's not necessarily better. Why is that? For example, if you run on a faster computer or the latest model, compare that to running it on a older model, then of course the other one would run faster, but it's not necessarily better, right? Same with using a low-level programming language that usually runs faster than a high-level programming language. So because of these factors, right? So there's too many factors that we need to consider. We need simplifications to make our analysis easier. And those three simplifications are what we will discuss today. So number one, we will talk about the RAM model, which we can use to analyze the algorithm without actually implementing it. Next, we will also use worst case analysis, so we'll assume worst possible type of inputs. And finally, we will also use big O notation, wherein we ignore unnecessary details of the running times equation. So why are we interested in doing this? Motivation is we want to analyze algorithms without worrying about the hardware and software differences. So we want to analyze algorithms without implementing them, and only by looking at pseudocode, we can actually determine if an algorithm is efficient in terms of running time and memory. Okay, so that we don't have to worry about the differences in setup and platform. Okay, and in this case, we can actually assume or assure that uh, the faster the faster algorithm is actually better, right? But in our analysis, why don't we use a real computer? The reason for that is a real computer has a lot of parts that are not essential when studying algorithms. So we want to strip down a real computer to a simple model computer with basic capabilities. But what are these basic capabilities? So in analyzing algorithms, we only need three essential parts. That is the working memory, input and output capabilities, and programming capabilities. The rest of the computer parts are not really essential in analyzing algorithms. So things like monitor, graphics card, mouse, keyboard, file system, OS, CD-ROM, and Wi-Fi capabilities, you don't need those when analyzing algorithms. Okay? So this is where our first simplification comes in, the RAM model, or the random access machine model. So it's a simple computer model which still has the main aspects of a real computer, namely the memory, the input-output capabilities, and programming capabilities. So the RAM will take input and it will process it, and maybe it will look at the memory. So it will access the memory and store items in memory. And after doing all the processing, it will give its output. Okay, so that's the RAM model. Now, let's talk a little bit about the RAM memory. So the RAM memory is divided into single cells. For example, look something like this. So that's one cell, and another cell. Okay, so RAM memory is divided into single cells. And each cell has a limited capacity. So you can actually only store one thing in here, right? So putting A, B, C, and so on. So each cell will only store one item, but you can have as many cells as needed. Okay, so in essence, you have an unlimited number of memory cells. Okay, now how about the time in the RAM? For RAM analysis, what we do is we count the number of time steps. So a simple operation like arithmetic operations take one time step. Loops count as often as they run. So that means that for each loop, you will have to count how many times that loop is actually being iterated. And finally, memory access is free. So if you're only storing a variable value or accessing a variable value, you don't take any time step for that. So memory access is free. Okay? So let's see an example. How many time steps does this code have on the RAM? So we have two lines of code here. We have A is equal to 1 and B is equal to 2 times 1. So the first line takes 0 time steps. Why is that? Because this is only a memory access, right? We're only storing the value 1 into variable A. But for line number 2, this will take 1 time step. Why is that? Because we have the arithmetic operation here, 2 times 1. So in total, that's 1 time step. Okay? Next, let's see a loop. How many time steps will this have on the RAM? So let's run it line by line. So s is equal to 5, and then while s is less than 0, we decrement s by 1. Okay, so the first line will have 0 time steps as well, because again, this is only memory access, which is free. Now, for this line here, how many times will this be run? So the inner part of the loop will be run 5 times, right? Because, well, s is equal to 5. So this will be from 5, 4, 3, 2, and 1. And the condition is that when s is greater than 0. So the inner part will run 5 times. So 5, 4, 3, 2, 1. How about the while loop? So this will actually be run 5 plus 1 time. So in total, 6 times. Why is that? So this is because for 5, uh, it will be run, 4, it will be run, 3, 2, 1, and then for s is equal to 0. Because it still has to compare if it's still greater than 0. So there's an extra 1 time step for this one. So in total, there are 11 time steps. Okay? So that's how you count time steps on the RAM. Okay, but even counting time steps is a little tedious, right? So later on, we will have a further simplification using the big O notation. So that will be for later. Now, RAM is only a computer model. And how does it compare with actual real computers? So which RAM simplifications are realistic? Number one, simple operations take one time step. Is that realistic? Number two, we have as much memory as we need. Is that also realistic? Memory access is free. And a unit of memory has limited capacity. So which among these four statements are realistic? In fact, only number 4 is realistic. A unit of memory has limited capacity. So that's true in real life. The simplifications 1 to 3 are not really realistic. So simple operations like arithmetic do not take one time step. So division will take longer than that. We don't have as much memory as we need because of course our memory is finite or limited. And memory access is not free because it also takes time to store and get data from memory. Okay, so there's a lot of unrealistic simplifications in the RAM. So if it has too many unrealistic aspects, why do we still use it? It's because the RAM is a simple model, and that makes the analysis simple too. And even with a lot of unrealistic aspects, the general behavior of the algorithm that's observed on the RAM is still realistic. Okay, so we'll still use the RAM even with the unrealistic simplifications. Okay, so that's the RAM model. Next, in some algorithms, the running time is also affected by the input structure, just like in this piece of code. So let's take a look at this one. So we are actually counting the number of A's in the string. So we initialize count is equal to 0, and for each character in the string, if character is equal to A, then we increment the count plus 1. Okay, so let's let n be the length of the string, and let's let A be the number of A's in the actual string. So how many time steps will this code have? Let's try to analyze it using the RAM model. So for the count is equal to 0, this will have how many time steps? This will have 0 time steps because, again, this is memory access and it is free. So for each character in the string, so this line will take n plus 1 time steps. Why is that? So note that we have n is equal to the length of the string. So of course, we will have n here, but it still has to check the last character, which is the end of the string. So we have the plus 1 for it to know that we can end the loop already. Okay, so there's a plus 1 to check the end of the loop. How about this one? If character is equal to a, so this line will be run n times because the inner part of the loop will run n times, 1 for each character of the string. Okay, and finally, the count plus is equal to 1. How many times will this be run? So it's not n times because it will only be incremented if the character is equal to a. So this will actually be run a times because a is the number of a's in the string. So if you have, let's say, 5 a's in the string, count will be incremented 5 times as well. Okay, so in total, the running time is 2n plus a plus 1. Okay, so that is our total running time, 2n plus a plus 1. So you'll notice that the running time is actually dependent on a, which is the number of a's in the string. And this is what we mean when we say that the running time is dependent on the input structure. Okay, so it's dependent on the input structure because it depends on the number of a's in the string. However, this becomes problematic because for more complex algorithms, the running time equation will be even more complicated. Okay, and in general, we really don't know what type of input the algorithm will receive. Will it have a lot of A's? Will it have like few A's only? We don't know. So to counter that, our solution would be just create assumptions about the input. So we'll assume things about the input so that we don't like guess. Okay, so for example, in our counting a's problem, recall that there's the running time was 2n plus a plus 1. What would be the fastest case in this problem? The fastest case would be if there are no a's at all, right? So that would make a is equal to 0. So if this is 0 here, that would make the running time only be 2n plus 1 because this one will be eliminated, the 0 part, right? How about the slowest case? The slowest case would be if the whole string is made up of a's, so all a's. That means that a is equal to n. In that case, our running time will become 3n plus 1 because if a here becomes n, that becomes 2n plus n plus 1. So it becomes 3n plus 1. Okay? So you'll notice that in both cases, we eliminated the dependency on a because our running time just depends on n this time. Wala na siya dependence on a, right? So that is what we'll do to eliminate our dependence on the input structure. we'll have to make some assumptions. So there are three views that we could take. We could be optimistic about it, and by that we mean we could assume that we'll receive the best input. So we'll get the minimum or the fastest running time. However, this is often trivial or meaningless because we don't necessarily get the best input all the time. Okay? So even if you assume that you'll get the best input, you're not guaranteed to have the best input. So we won't use the optimistic view. The next one, we could have the average view. We'll assume that we'll receive the average input. So we'll get the average time. It's a little interesting to get the average view. However, it's hard to define what average is. So for example, in counting A's, what is the average number of A's in a word or a string? We don't know, right? So it's really hard to define what average is. The last one is the pessimistic view, wherein we assume that we'll receive the worst type of input. And doing so, we'll get the maximum or the slowest time. And this is the view that we'll actually use. So we will use worst case analysis. So we will assume that we will receive the worst type of inputs. And the advantage of doing this is that it will give us an upper bound, or it will guarantee that the algorithm cannot take any longer than the worst case running time. That is already the upper bound limit, so it cannot exceed more than that. Okay? So we will use worst case analysis. So for our simplification, if our RAM analysis depends on input structure, just like what we had in our example of 2n plus a plus 1, we could assume the worst possible inputs to remove the dependence on the input structure. Okay, so we'll assume worst possible inputs. Okay, so that's the second simplification. Now, in our analysis earlier, we noted that it's still tedious to count every step that the algorithm makes. For example, if you have a running time of 2n squared plus 23 and another running time of 2n squared plus 27, it's only a difference of 4 time steps. So we can say that they're essentially the same running time, right? So only a difference of 4 time steps. Maybe we don't care about that. So let's see another example. Which algorithm is preferable in general? Algorithm A's running time is 3n squared minus n plus 10. Algorithm B's running time is 2 raised to the n minus 50n plus 256. So which algorithm do you think is preferable in general? In general, algorithm A is preferable. For small inputs, algorithm B might have the same running time or even better. But we don't care about the small inputs or small test cases. We only want to examine the behavior in general. Okay? So when we compare the two running times, we have to remove the unimportant things. So for example, we could disregard the plus 10 and the plus 256 because anyway, that's just a constant difference. We could also disregard the minus n and the minus 50n because anyway, they have the same order, like order of n. And we can also disregard the factor 3 from 3n squared. So really what we're left with is it n squared versus 2 raised to n? Okay, so algorithm A is essentially n squared and algorithm B is essentially 2 raised to n. That is why we chose algorithm A to be better in general because n squared is faster than 2 raised to n, right? So this is where big O notation comes in. So big O notation takes away unnecessary things when comparing algorithms, and it allows us to focus on the main components of the running time. What is the main component of the running time? It is the growth rate of the running time. So what is the growth rate? As input size n grows, what happens to the running time? So let me graph here. So let's say that this is your um, so this is the input size, and this is the running time. So as n grows, like so, as it increases here, what happens to the running time? If it's a slow growth, that means that it's good. So that means that even as we increase the input size, ang running time niya doesn't really increase fast. So it has a very slow growth rate. So that one is good. Okay. But if we have like a fast growth, that is bad. So for example, as we increase the input size only by a small amount, and then the running time already increases a lot, so it has a steep growth rate, this one is bad. Okay, because even if for a small input size here, ang running time niya is already up here. Compare that to the slow growth rate na if the input size is here, the running time is still here. Okay, so that is what we mean by the growth rate. So slow growth is good, fast growth is bad. So formally, definition of big O notation is the following. Given two functions f of n and g of n, if g of n grows faster than f of n, then there exists a number m and a constant c such that c times g of m is always greater than or equal to f of m, and for all p greater than n, we have g of p is always greater than or equal to f of p. So if the conditions hold true, we say that f of n is in O of g of n. So we read that as f of n is contained in big O of g of n. Okay, so this seems like a mathematical way of putting things. Let's see what exactly that means. So if let's say we have two functions here, this is f of n and then this is c times g of n. So there could be cases wherein f of n is bigger or f of n is smaller than g of n. So in some cases, pwedeng their behavior is still mixed up. But at some point, at some number m here, c times g of n will always be bigger than f of n. Okay, so we say that g of n provides like an upper bound to f of n. So g of n grows at least as fast as f of n because g of n has a faster growth rate, which is bad, than f of n. Okay, so that's big O notation. So let's see some examples. So 3n plus 1 is in O of, well, O of n, right? 18n squared minus 50 is in O of n squared because that is the biggest growth rate here. 9n to the fourth plus 18 is O of n to the fourth. 30 n raised to 6 plus 2 raised to n plus 123 is O of, well, it's not n raised to the 6, but it's actually O of 2 raised to n because 2 raised to n is the bigger factor than n raised to 6. Okay? So don't be confused by that. It's not necessarily the first term, it's the biggest term. Okay? How about this one? 2n squared plus 30n raised to 6 plus 123. This will be O of, well, it's not only 2n, but it's actually 2n squared. Because this one is different from just plain 2 raised to n. Okay, so it's 2n squared. Okay? Now, how about this one? 3n plus 1 is in O of n squared. Is this true or false? Well, it's actually true. Why is that? It's still true because n squared still grows at least as fast as 3n plus 1. So that means that n squared is still a bigger function than 3n. So 3n plus 1 is still contained in n squared. However, the bound is not as tight as possible because the tighter bound would have been O of n. How about this one? 18n squared minus 50. Is it in O of n cubed? Well, yes, because n cubed is a bigger function than n squared. Is it tightly bound or not? It's not. If it's not tightly bound, what is the tighter bound? The tighter bound is O of n squared. Okay? So hopefully that's clear. So our big O notation describes the growth of the function while ignoring unnecessary details. So we'll only concentrate on the fastest growing part of the running time equation. Okay? So the correct notation for big O is f of n is in O of g of n. However, we kind of also accept f of n is equal to O of gn. But technically, this one is the correct notation. Okay? So the common mistake is thinking that big O is an approximation. It's not. Okay? It only provides an upper bound. So it's a upper limit for your function, but it's not an approximation. So big O notation is actually part of your asymptotic analysis. So asymptotic analysis is the study of asymptotic efficiency, wherein you only look at large enough input sizes so that only the running time's growth rate matters. So if you recall um, from this one earlier, from this figure, so we really don't care about the small uh, input sizes. So we only care about big enough input sizes, like for example, after m, such that only the growth rate matters. Okay, so that is your asymptotic analysis. So an asymptotically efficient algorithm will be the best choice for all inputs, except for a few small cases. So as we noted earlier, the bigger function could have faster running time in small cases, but we really don't care about that. We only care about big enough input sizes for the general behavior. Okay. So asymptotic analysis is a way to describe and compare behavior of functions in the limit. This is from asymptote, which means a curve limit, right, in your calculus. And it allows us to focus only on the growth rate, and we ignore low order terms and constants. So just like what we did with big O, right? We ignored the unnecessary details. So we already know about the big O notation, but there's 4 other asymptotic notations, namely your big omega, theta, little o, and little omega. So we'll only briefly cover these 4 other asymptotic notations. So for example, for theta notation, this means that it's the asymptotically tight bound. Okay, so this describes the average case. Ang little o notation naman provides an upper bound, but it's not asymptotically tight. What does that mean? For example, n squared is not in little o of n squared anymore. Whereas if it's in big O, this would have been true, right? Instead, n squared is in little o of n cubed. So it has to be a bigger function, not equal, because in big O it was bigger or equal, right? So greater than or equal. Here it's strictly greater than. So sa big omega naman, it's the opposite of big O. It's the asymptotically lower bound. So it provides the best case running time, and the opposite, the little omega, is a lower bound but not asymptotically. So similar sa little o as well. Okay, so those are the four other asymptotic notations. But for this class, we'll focus on big O notation lang. Now, let me run through the common growth rates that we'll encounter. So I think we have 7. So first is the constant growth rate, or O of 1. So we use this for simple operations like arithmetic operations, so one-liners basically. Okay, so adding two numbers. So that's constant running time, O of 1. Next, we have the logarithmic running time, or O of log n. So this is when we try to divide in half, like in binary search. So the code for that will look something like this. So while n is greater than 1, then you divide n by 2. So it will be divided by 2 each iteration. So for example, from 16, it becomes 8, it becomes 4, it becomes 2, it becomes 1. So that is a logarithmic running time. Okay. Next, we have the linear running time, or O of n. So this is commonly seen when we loop through n items. So like finding the maximum, for example, then we have to loop through everything to find the max item, right? So it looks like this. For I from 1 to n, then you do something along that loop. Okay, so that's linear. Next, we also have the linear rhythmic, or the log linear running time, which is O of n log n. And we usually see this in divide and conquer algorithms like your merge sort. So you'll learn more about this in your ComSci 142 next semester. Next, we also have the quadratic running time, or O of n squared. And we usually see this in double loops, or double for loops, okay? Like checking all pairs, for example. So if you see something like for I from 0 to n and for j from 0 to n, which is a double for loop, then that's usually a quadratic running time. Okay, because the outer loop runs for n, and then the inner loop runs for n each time as well. So that's n times n squared. Okay. We also have the cubic running time, which is n cubed, and you usually see this in triple for loops, like checking all triples. So similar sa example earlier, so for I from 0 to n, for j from 0 to n, for k from 0 to n. So you have 3 levels of loops nested within each other. And finally, the worst of them all is the exponential, which is O of 2 raised to n. So you usually see this when you have an exhaustive search or brute force na search, like checking all possible subsets. Okay, so yeah, those are the 7 common growth rates. And we'll see them in the graph here. So the constant running time is just flat, and even the log of n is also almost flat. Then you have O of n here, which is the green one. Then n log n is here, so it also has a fairly average growth rate. And then when you have the n squared, you have a pretty steep growth rate already. And then n cube is even steeper, and 2 raised to n is also here. So medyo steep na siya. Okay? Those are the common growth rates. So what are the practical implications of this one? If you have a faster growth rate, that limits the size of the problems that you can solve quickly. So for example, if your problem size is 30 and your running time is O of n squared, then it will be done in 900 time steps, because 30 squared is 900. But if it's O of n cubed, then it would be 27,000 time steps already. So just imagine from less than 1,000 to 27,000, that's a big difference, right? And if you have the exponential running time with n is equal to 30, then you'll have a billion time steps already. So it's really important to keep your running time within either linear or quadratic siguro, no? Or if cannot be avoided, cubic. But as much as possible, try to avoid having exponential running time, because it really, if you look at this one, the orange part, it's a really steep growth rate. So even just a small difference in the number of items, the running time is increased by a lot. Okay, so yeah, so that is running time analysis. And before we end, let's briefly cover how to analyze auxiliary memory as well. So auxiliary memory refers to the extra memory that we need. It doesn't include memory that we need for the input, so that's already built in. But what this includes are variables and data structures that we need uh, for our algorithm. So extra na memory. So let's say, for example, for this one, the extra memory that we need is only O of 1. So it's constant because we only have, for example, for this one, this is only two variables, right? And two variables is just constant. How about for this one? So new data is equal to an array, and for each item in the data, we'll append item times x when we increment x each time. So the memory for this one is O of n, because we have an array that also has the same size as the data that we have for our input. Okay, so it basically has the same size because we add each item in the data to the new data as well, but this time it's processed by multiplying it to x. How about this one? So new data is equal to an array, but for I in input data, we also initialize new data I to a new array, and then new data ij is equal to the product of I and j. So this will actually take O of n squared, because this time we have a two-dimensional array. Okay, so it's not only a one-dimensional array. Inside each array item, you also have another array. So n squared na siya. Okay, so that's it. So to review, we talked about the RAM model, which we use to analyze algorithms without actually implementing them. And even if they have a lot of unnecessary, or not unnecessary, but unrealistic simplifications, we still use them because the behavior of the algorithm in the RAM model still applies to real life. We also looked at worst case analysis, wherein we assume the worst possible types of inputs so that we could have like an assumption, okay, on the type of data that we'll get. And we can actually remove the dependence on the input structure. And finally, for big O notation, we ignore the unnecessary details like the lower order terms and constants, and focus only on the growth rate of the algorithm. We also looked at some asymptotic notations. So big O is less than or equal, so it's the upper bound. Big omega is greater than or equal, so it's the lower bound. Theta is equal, little o is less than lang, and little omega is greater. So that's it for this video. I'll see you next time.